Okay, we'll now complete this with a implementation of the Adt heap. So I have a hash define which gives the size of the heap, and type def and putting integer here. Again, you can use an element type.h as we had taught in the last class. And I'm using a type def int position just as before. And position, why is this required? This is required to point to the last element in the heap. So I have a class heap here, and this heap is made up of elements of element type, which can contain the job ID and the priority. And of course, right now I'm assuming both are the same. It's not correct. I'm assuming that I'm only worried about the priority. Insert heap inserts an element into the heap, deletes an element from the heap and reheapifies. Empty checks whether the heap is empty, and create heap and print heap if you want. And what I do is insert elements into the heap. So what are we doing here? We notice that we initialize, let's create heap. Okay. Maybe I don't have the create heap here. Yeah, create heap. I initialize this last to 0 because I'm inserting elements from 1. Then I increment last, and I set I equal to last, and while I not equal to 1, and while the priority of a given element is greater than priority of I by 2, you keep moving the elements down. And finally, you reach the position. Just it's very similar to insertion sort. Okay, it's just that the indices move in terms of you start with an initial position at I, divide by 2, then next divide by 4, and so on. And that's why you get the log in over here. Push it in its appropriate position. Delete. What do? We just do the reverse. We're removing the first element in the array. Then what we do is we take the last element which is there, we reduce the size of last, and we compare. Notice this way, we ensure that whichever guy's priority is, whichever left child or right child priority is higher, we increment child over here. Child was a 2 or 2 plus 1. Then you take the stem which corresponds to the last element, and you move it to its appropriate position in the heap, and then you increment child by its parent times 2, so that you keep moving down the tree, which essentially does the heapify. Then finally you put it in its appropriate position in the tree. Okay, so this is essentially a very, very simple implementation of heaps, but there's one major drawback of heaps is that we do not have when I was talking about various types of heaps a little while ago, the one major drawback of heaps is that one major drawback of heaps is that ideally, you want to keep the job ID ordered, and also the priority ordered. Okay. We're going to next learn about another type of tree called the binary search tree, where we will not worry whether it's complete or full or whatever, and we will organize using job ID. But of course, it's not going to be in terms of priority. So you learn in your next course another tree called the tree It's called a tree heap, and which is both heap ordered and tree ordered. Okay. Because what you would like to do is you'd like to get rid of the job itself, right? Once you delete job is removed, you want the job ID also to go out of the system. Okay. So this kind of completes all that I want.